Was it 28? Not sure. I think it was something else. I think 22. I think it was 22. Was it for the quiz? Last time we had question. I believe it's 22.
It was 24.
24. Oh, thank you. That's even better. So not 22, 24. So it says heater is working. So it looks like we should compare this statement with one of these four, and looks like there is a one that deals with a heater. It's part S, the fourth statement here. But this statement negates the fact that heater is working. So I just need to say not S. Or some people put that little wiggle in front of S. So you could also say this is like this thing, right? Because once again, statement that we have in 24 says heater is working. So it is indeed working, but if I wanna write this using that S statement, well, then it'll be the opposite to S, because the S says it's not working, or it is not true that heater is working. So if you cross out not, it will get it is true that heater is working. Well, looks like that'd be exactly the same with 24. So I negated S and produced 24. So that's all they wanted. Well, I know that might confuse some people. That's why I'm saying that problems in this section are a bit unusual. But since there are various sentences and sometimes you'll get lost in them. Well, in the next sections, it'd be more straightforward. So let us actually take a look at the next section, because here just one fact that we had to get used to, that if you want to negate, to say no, well, you could just put this wiggly little symbol, and that's called notation. So there are some more symbols that the next section provides for us, and those will very closely correlate with Venn diagram. For example, if you recall how we treated intersection of sets A and B, well, very similar idea will be for this so-called conjunction, that a way to produce the logical idea for and A and B, so they both work at the same time. So I would say the analogy, it's not exactly the same, but it's analogous to statement P with a Q. It's just like the common part, the intersection. So you can think of it this way. And if you think in terms of Venn diagram, then it's always going to be intuitive rather than just getting some of these statements in here. So analogously, we have statements with or. So that's what the next portion of section is talking about. And we already saw unions for that matter, right? A union B, that was or A or B, so you can be in any portion of either set A or set B. And turns out for that, they have a special logical symbol also that's called disjunction. So there's a word for this is, well, I guess just a logical word. So one should be familiar with the word disjunction or conjunction. In fact, they're actually spelling it out here on the bottom of the page. So analog of and or intersection. and analog of or is a union. Well, that's, I think, should make us feel a little bit more comfortable with this. So you can always relate this to what we have already saw in the previous chapter, in chapter 2. Let me clean this a little bit. So it turns out there is some more logical notations that we actually didn't really see in the Venn diagrams. And that's the one that says if P, then Q. So if P works, then Q. And there is a special symbol for that, which is called from P follows Q. So that's the interesting case that people usually encounter when they take, say, computer science classes. They try to learn computer programming, and that way we get this so-called implication. That's the word for that statement, implication. So they put this down below on the table. And looks like if you start to read whatever they put here in words, you might start to get a bit confused. So that's why I'm going to try to avoid all that. But it's good to realize that statement from P follows Q could be written various ways. Actually, could be spelled out in English language various ways, such as if P then Q. That's probably the most straightforward way, but you can start on the right and go to the left. So you can say Q if P. So instead of going one way, you're going backwards. So you start here at the end and then produce Q. Or you can say P is sufficient for Q. So if P happened, then Q. So that's probably pretty straightforward. Now, there is another way that says Q is necessary for P, and that's a little bit obscure. And there's two more. So I guess there are various ways to say the same thing, but I would always prefer the first way. So if P, then Q, so that way everybody can clearly see what is going on. So I guess that's the message. So I'm going to try to make this be pretty straightforward. So that way we'll see everything in a much better, I guess, and clear position. So anyways, there are various statements that appear in logic. Please notice that you can go backwards and you can say that from Q follows P, and that's what we just observed in the previous page among those examples. And it turns out if both of those work, then you can say that P is equivalent to Q. So there is a special double arrow right here that they are also talking about. So it looks like they just want to introduce us with various symbols that we'll see in chapter 3. And my goal will be not to hurry through this and just little by little get used to those symbols. I know it may be sometimes a little bit not as straightforward, but the idea is that this double arrow in this case means that you have end arrow going from P to Q, and at the same time the arrow that returns back from Q to P. So that means that two statements are actually equivalent. And so in logic, they say this if and only if. So that's another thing that we're still thinking about. Well, anyways, looks like they coming up with various notations for chapter 3 that, well, eventually we'll get used to. And looks like those are all nicely put together in a table 3.8 here. So in this table 3.8, we see all of them. So the one that we just utilized in the previous section called negation, and that's the one that says not P. So that deals with one statement. So we negate it, we just put not in it, and that's it. Well, then we start to deal with two statements, and we can either think of their intersection or union analog, or we can have a conditional statement, then from first follows the second. And there is also biconditional statement, which means they're actually equivalent statements. So from first follows the second, and at the same time from second follows the first. So this arrow could be put in either direction. So those things are good to realize. In fact, biconditional statements are very popular when we're dealing with so-called definitions. We deal with definitions. So for example, let me come up with something by myself. If you have a set of natural numbers, do you ever see this notation? So the numbers that we use here are 1, 0, not 0, 1, 2. After 1, we have 2. I need to wake up. 1, 2, 3, 4, 5, 1, 0. Come on, Alex. So we have these numbers that we use to count subjects, 1, 2, 3, 4, etc. So set of naturals. And when we put the equal in between, it means it goes biconditionally. What does that mean? So say if we in n, then we are in this 1, 2, so one number of this. But you can also go backwards. So you can say if we are in this set, then we are in n. In other words, we can put equal in between of those two sets. So if we're in naturals, then we have to be here, or if we're here, we're in naturals. So it turns out that biconditionals, you actually do see a lot. They just never tell us that this is biconditional. So whenever we have word definition, it's always biconditional. And that's interesting to think about, because lots of times people don't really know about that. So anyways, there are various examples that they're looking at in this section. And here, some of those, like P and Q, for example, there are various parts in here. So one says, she is wealthy. So that I'm looking right now at this part. P, she is happy. Q. So of course, there are always some cases when you say some wealthy are not happy, or some happy people are not wealthy. So that's why they're trying to talk about this. But since there are so many possibilities, it's kind of hard, right? Because you can always come up with a person that may not fit description. But that's not what they want here. So they don't want you to start to come up with any of examples from real life situations. They just want to negate P and Q. So it'll be, if you negate P and Q, then first you need to know what does P and Q mean, right? It looks like I already have the idea of that here with Venn diagram. So it'd be just common parts. So you can think of those wealthy people that are happy and vice versa, those happy people that are wealthy. So it looks like we're not considering everyone. We're just considering only part that belongs to both categories at the same time, right? So we can also look at negation of that statement, negation. So we can say not that. And looks like for negation, I can imagine myself another Venn diagram. And this will give us intuition on what they're trying to say. So if I going to think of this red set that I produced as intersection, right? So this red set was the intersection of those two. Then everything that is not, so everything that is not there will be in negation, right? So if I want to negate this P and Q, I say no, I take a complement, remember the word complement. Well, then everything that is not in the overlap, that is not in their union, is going to be in that part. So how can I write this with words? Well, looks like you say not she's wealthy and she's happy at the same time. So we're looking, in other words, at all people that in a complement of being both wealthy and happy. So this could be a person that is not happy, not wealthy at the same time. So those are going to be probably people here. Or it could be a group of people right there, which is going to be wealthy but not happy. Or people here, happy but not wealthy. So it looks like there are lots of things if you try to put them in words. But with Venn diagram, it's pretty straightforward. So once you made a picture, then you don't even need to explain it much because it's all in front of you. So I think that's the whole point of this story. So they're just trying to relate the statements to the various sentences. And well, I would say this section is kind of introductory. I used to always get into this, and I always had people in class that were panicking and losing track because there's sometimes some English statements that may not be very clear. And that's the reason why I will skip this section. Section 2 of chapter 3, I just give a bit of introduction, and I'm going to skip it because same exact story will appear again on the section 3.3. So it's worth to look at 3.3 first, I believe, and then we can, if we want, take a look at 3.2. So 3.3, I think, is pretty straightforward from mathematical perspectives. And it teaches us how to produce so-called truth tables. What does that mean? Well, if I have a statement called P, it could be just any statement. So I'm looking at analog of example, which is considered here. Well, it turns out this statement could be either true or false, because this is a statement. Remember, we gave definition of statements. We said that if it's either true or false, well, then it's a statement. Cannot be both at the same time, or neither at the same time. So now what I want to do is negate P. So I'm going to put this not P in here. So how would I do this negation? Well, if statement is true, if I said not true, it's going to be false. So when I negate the truth, it's going to be incorrect, so it'd be false, right? And analogously, if I have a false statement, if I negate it, it's going to be true. So it's either true or false. If I negate one, I get the other. So that's how we produce so-called truth table. So what is the point of doing it? Well, the point is to make sure that you show all of the possibilities here. So nothing is missing. So it could be either true or false. And well, we just listed what happens in either case. And that's just what I need. So it's nice and short, truth table. Of course, there'll be a little bit longer ones. And that's what I'm gonna see here for the next operation called conjunction. So let me get truth table for this conjunction thing. And it's a good idea to do it here on the left side because that's where conjunction is. So it turns out there are 4 possibilities that I have to consider because there are 2 statements, P and Q here. So notice that P may be true or may be false. We don't know what it is. Just like in the previous example, we had 2 choices because it's statement. Could be true statement, could be false statement. We assume that P and Q are totally independent. One has nothing to do with the other. So Q can also be either true or false, right? But in the case when P is true, Q can be either true or false. Or in the case if P is false, well, Q doesn't care. It could be either true or false. And that's why people say there could be both true. See, I produce so-called tree diagram, just like a little tree that I can start here and just go along the branches. So they both could be true. So both P and Q could both be true. Or here's another branch. If I go T and then down F, then the P could be true, but Q could be false. So I just want to list all of the possible cases in here. So I go down and go along another branch, and I see that we may start with a false for P and true for Q. And finally, very last branch, both of these could be false. So people put this 4 possibilities to create the true table for P and Q operation. So what they trying to do in this cases is to justify when it is true, when it is false. And it turns out the only case when it is true is going to be here. When both are true, in other words, when you are in both sets at the same time, N and P, N and Q, if you look at the Venn diagram, you're probably going to better see it. So if you're in both here and their intersection, then you can say that, yes, I am in the intersection. And if you're not in both sets at the same time, so you may be here, then you're not in the intersection. So you're saying it's false for intersection. Or if you're here, you're not in the intersection either. So it's false for the intersection. Notice that here we had true for one, and there we had true for the other. So we were in one, but not in the other. And of course, the case when you're on the outside. So both are out. So both are false, means you're not in either set of this. It's also false. So that's a definition of conjunction. And it's right here on table 311 on the bottom. And all one needs to realize is that it gives the result true only in one case, when both of them are true. I think it takes a little time to get used to these tables. And what you need to realize is that we care only about the last column. First 2 columns are the ones that we will always have for all of our examples here. And the last column actually tells us the answers that we produce at the end. So when I start to think about another operation, which is called disjunction, I will produce exact same little table. So there'll be PQ here, and I care about now result of P or Q. And PQ are always going the same. So both T's, then we have TF, then I have F for P, so it'll be FT and finally FF. So please notice it's exact same as for the previous table for table of conjunction, because we have this copied exactly the same. And that's always going to be for these little definitions. So now I need to decide where I get those true or false results. And it turns out the only case when I'm not going to be in the union when I'm on the outside. So I'm not in either of these sets. So it's going to be the last one. So when I say false to first, false to the second, so we're neither in those two sets. So we're on the outside. And whenever we're either here or here or here, we're in union. So we get true for all of those. So true means we are there. False means we're not there, if you look at the Venn diagram. And that's actually what they talk about on the next page with a definition of disjunction. So notice that's the exact same table that I just produced that has only one F for the very last one. And everywhere else we have T. And please notice that once again, this part of the table is standard, so it's always same. So always have T, 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 F, F, T, F, F. So it's left side is just a start, and the actual definition of disjunction is here. Well, producing those definitions and true tables is something that we're going to practice within next weeks. So you will get used to it. So no need to worry. I just want to look at some of the exercises in here so we can start to get used to production of this so-called truth tables. So let me go to the section end and maybe do some of the exercises. So let me clean this mess first. Clean this middle part. And start with the beginning. So I'm not planning to hurry here. I just want to do this carefully so we all get used to it. So like exercise number 1 here. It says not P. So what does that mean? Well, for not P, I'm going to have statement P, which is 4 plus 6 is equal to 10, right? But crossed out, right? 4 plus 6 is not equal to 10. Is that right? Well, 4 plus 6 is 10, so that's false. Actually, I was doing exercise number 2, sorry, not exercise number 1. Okay, so I did exercise number 2. So not P means we're negating, right, the fact that 4 and 6 added give you 10. But it is not correct, it's false, because 4 plus 6 is indeed 10. And that's all it is. Interesting, right? So that's worth to think about. So it's either true or false for each of those. So let me try another one. Let me try maybe exercise 3 that says P and Q. So what would that stand for? P and Q. Well, you have P, which is a true statement, right? Because 5 plus 6 is indeed 10. And you have a Q. So is Q true statement or not? Is 5 times 8 equal to 80? No, it's a false statement. Okay. So I have 2 statements here. One of them is correct and the other of them is incorrect. And it turns out that I should be looking now at the table here with P and Q, right? P and Q, and finding that when P is true and Q is false, please notice that first is true, right? And the second is false, then together they give us false. So I just pulled this from my table. And again, the table that has true for P and false for Q, and that's what we just figured out. So it's interesting. How about if I try one more here? How about if I try number 9? I just started in this section, so I think we need to spend more time on it next time. So no worries, we'll just start this section. So Q or P. It looks like now we're to look at the other table with or, which is here on the right side, Q or P. And once again, they told me that P was true, right? And Q was false. So what's the result? True. That's all it is. How about that? Can you tell me what's for problem number 1? Is that true or false? I think that'd be interesting. So I'm glad that you're working also. That's good. I totally agree. So it looks like the quiz exercise will be number 1 problem. So all you have to tell me either T or F. So what do you think? Not Q. Would that be correct or incorrect? So is that going to be true or false for negation of Q?